Dielectrics. Capacitance can be increased by inserting a dielectric, or an insulator, into the gap. The atoms in a dielectric are slightly polarized. The electrons are not uniformly distributed, resulting in a separation of charge. Before the plates are charged, the group of the dielectric's atoms are unpolarized, and each atom points in a random direction. When the plates are charged, the atoms line up with their negative ends closer to the positive plate. The dielectric material becomes polarized. An internal electric field is now generated by the dielectric that opposes the electric field from the top plate to the bottom plate. So you can see here that these little atoms have arranged themselves so that the negative side is pointing towards the positive plate, which creates a little electric field from positive to negative that points up, while the main electric field in the capacitor points down. On the diagram, the electric field lines in red are due to charges on the plates. The electric field lines in black are due to the polarized dielectric material. The strength of this internal field depends on the dielectric material. The overall effect is that the dielectric reduces the net electric field for a given applied voltage. This is helpful because if the electric field between the plates gets too large, it will cause a dielectric breakdown in that space. So here in red you can see the original electric field between the plates. However, with the dielectric, we now have this little electric field pointing the other way, reducing the net electric field. A dielectric breakdown enables charge to flow directly between the two plates, a similar effect to lightning, or the sparks you get when you touch a doorknob after rubbing your feet on carpet. This is not good. If this happens, the capacitor is now discharged and will not store energy. It can also harm the circuit or a person touching it. While a battery releases energy relatively slowly, a capacitor can release its energy almost instantaneously, which can be very dangerous. The dielectric material was originally neutral. Once it became polarized, this reduced the strength of the electric field, which lowered the electric potential difference. To again reach the potential difference of the battery, more charge was stored on the plates. Thus, the total charge in the capacitor increased. The voltage stayed the same, since it's still connected to the same battery. Since capacitance equals charge divided by voltage, the capacitance of the configuration increases. An engineering benefit to a dielectric is that it insulates the plates from each other, and thus the distance between them may be made very small, and charges will not flow between the plates. Every material has a dielectric constant, kappa. A sample table of values is shown to the right. For a vacuum, kappa equals 1, and the dielectric constant of air is about 1. If a dielectric is present, our equation for capacitance becomes this. The larger the value of kappa, the larger the capacitance. We've only done problems with air in between the plates, which is why we have not yet included this. This has been 1 in all of the problems we've previously done. But now it can be something else. Silicon is a very good dielectric to put in between the plates. There are 3 key equations that describe the physical nature of the capacitor: the charge stored, the voltage between the plates, the stored energy, and the power available. The AP Physics 2 exam asks what happens to these variables when a different voltage is applied, or if the physical nature of the capacitor is changed. The capacitor's plate area, or distance between the plates, can be changed. A dielectric can be moved in or out of the plates, affecting the dielectric constant kappa. This is the only way to change the capacitance. No matter what voltage is applied to the capacitor, C will remain constant. C only depends on physical characteristics of the capacitor. Capacitance is increased by adding a dielectric, increasing the surface area of the plates, or decreasing the separation between the plates. Capacitance is decreased by removing a dielectric. decreasing the surface area of the plates, or increasing the separation between the plates. Be careful. If these variables act against each other, you need to calculate the total impact. Many times the problem just changes one of these characteristics. Next, the problem will probably state that the capacitor is either still connected to the battery or the capacitor was removed from the circuit and is isolated. If the battery stays connected while the physical characteristics of the capacitor are changed, whatever the voltage was across the capacitor remains the same. That's conservation of energy. If it's just the battery and the capacitor, the voltage of the battery equals the voltage across the capacitor. For multiple resistors, the battery voltage may not be the voltage across the capacitor. The capacitor voltage will equal the voltage of the resistors that it's in parallel with, but we have not covered this yet. This will be in the next unit on circuits. If the capacitor is removed from the circuit, the charge on the capacitor will remain the same, conservation of charge. It has nowhere to go. However, the voltage will change. Now the problem can be solved. First, calculate the new capacitance. 2. Use the formula C equals Q over delta V, or on the AP2 equation sheet, it's delta V equals Q over C. If the capacitor is still in the circuit, that means delta V remains the same, and if the capacitance increases, then the charge increases. If capacitance decreases, then charge decreases. If the capacitor is removed from the circuit, charge remains the same. If capacitance increases, then the voltage difference decreases. And if capacitance decreases, then the voltage difference will increase. These equations are true for all capacitors. Delta V equals Q over C. The energy stored in a capacitor is 1/2 QV. It's also equal to 1/2 CV squared. It's also equal to charge squared over 2C, but this equation here at the end is not on the AP2 equation sheet. The following equation is true for parallel plate capacitors, as it depends on the specific geometry of parallel planes. Unless indicated otherwise, kappa is going to be equal to 1. Combining these equations can solve many problems related to the voltage, charge, electric field, and capacitance of a capacitor.